Jai Hind to all. My name is Amit Kumar, Assistant Professor in Electronics and Communication Engineering Department. Today we have discussed the combinational logic circuits. As we know, logical circuits are the two types, combinational logic circuits and the sequential logic circuits. In the combinational logic circuits, the output depends only on the present input and not depend on the past input or the past outputs. So, combinational logic circuits have not the memory. Combinational logic circuits have the examples half adder, full adder, half subtractor, full subtractor, encoder, decoder, multiplexer, and magnitude comparators, etc. So today in this lecture we have discussed the topic half adder. Half adder half adder having the two inputs, suppose A and B, and the two outputs, that is the sum and carry. Half adder is a logical circuit that's taking the 2-bit additions. A and B are the inputs and C and S are the outputs. Thus the inputs and is the outputs of a half adder. Now here we see it is had the two inputs A and B and the outputs having the terminal S and C. S stands for the sum and C stands for the carry out, or sometimes also we can call the carry simply. Now we develop the truth tables. Truth table is nothing but to give the input output relationships of a logical circuit. In the inputs we have the A and B, and outputs are the sum and carry. By taking the two inputs we have the total number of combination, that is 4, means 2 raised to power 2 equals to 4 combinations. So by taking the two inputs A and B we have the 4 combination like this 0 0 1 1 0 1 0 1. So since here A equals to 0 and B equals to 0, then if we add 0 plus 0, then sum goes to 0 and C carry also goes to 0. When we add A equals to 0 and B equals to 1, then sum goes to 1 and carry goes to 0. When we add A equals to 1 and B equals to 0, then sum goes to 1 and carry goes to 0, that is low. When both the inputs are high, means equal A and B are having the logical 1, then the output sum equals to 0 and carry goes to high. In this case output of the carry will be high and sum goes to 0. So now we find the expressions for the sum and carry. For finding the expressions for the sum and carry, we use the Karnoff map, that is called the K map. So expression of sum because we have the two inputs A and B, so we take the 4 cell K map. For the finding the expression for the sum. So here we have the a equals to 0 equals to 1, b equals to 0 and b equals to 1. From the two tables we see that the sum is only 2 times as high, here and here. Sum is only 2 times high. When a equals to 0 and b equals to 1, then sum goes to high, and when a equals to 1, b equals to 0, then sum equals to 1. So these entries are filled in the K-map cells. So when a equals to 0 and b equals to 1 here, and again when a equals to 1 and b equals to 0 here, this one. So there is no pair possible, so we make a individuals, this one also. So now we write the expressions for the sum s equals to this one. After simplifications of the K-map, we get a dot b complement plus, and for this one we have a complement because a equals to 0, and b a complement dot b. So this is nothing but only the XORing of a and b. Now similarly we find out the expressions for the carry. Now for the carry out, again similarly we develop the 4-cell K-map for the carry out expressions. This is again 4-cell K-map for the carry out expression, or simply carry expressions. So here we see that from the two tables, carry is single time high. When carry is high, then the inputs both a and b are high. Both the inputs a and b are high. So we fill this entry in the K-map cell here. And there is no pair, no quad, no octet is possible. So we make a single individual in the K-map. So expressions for the carry C equals to A, because A having the value 1, and B because we have the value 1. So answer becomes to A, B. So from the two tables and with the help of the K-map, we find out the logical expressions of the sum and carry. Sum equals to A XOR B, and carry becomes equals to A dot B. Now we develop the logic circuits of the half adder. Because S equals to A XOR B, which having the inputs A and B. A, B, S equals to A XOR B equals to A complement dot B plus A dot B complement. Now again we have the expression for the carry, that is equals to A dot B. So A dot B is nothing but that is the ending of A and B. So we take a AND gate here, 2 input AND gate. And make the connections from the inputs A and B. Inputs A and B, that's a AND gate and that becomes the output carry equals to A dot B. So that's the AND gate and that's the XOR gate. So this is the logical circuit of the half adder. So in the half adder we having the only two single bits and we find out the sum and the carry as a outputs. Now another examples of the combinational logic circuit is full adder. That's the next one we have discussed now, full adder. Now we have discussed the full adder. Full adder is a logical circuit that add the three single bit and produce the output again sum and carry. In case of the full adder we have the three inputs A, input A, input B, suppose, and the input carry in, C in. A, B and carry in. And again two outputs, that is the sum and carry out. S and C out. So in case of the full adder, here we see that we have the three inputs A, B and C in and the two outputs, that's the sum and carry output. So now we develop the truth tables of the full adder which having the three inputs. That's the input side and here we take the output sides. In the inputs we have the three inputs A, B and C. So we write the input here A, B and C in, and we have in the two outputs sum and carry. So in this side we write the sum, that is S, and the carry out, that is the C out. So by taking the three inputs A, B, C in, we have the total number of combination, that is 8. 2 raised to power 3 equals to 8. So we develop the 8 combinations of the 0 and 1 in our truth tables like this. So these are the entries of 8 combinations on the input side. Now when we add A, B and C means 0, 0 plus 0, then sum goes to 0 and carry also goes to 0. Now again second entry, when we add A equals to 0, B equals to 0, C equals to 0, then sum goes to high and output, that is C out, goes to low, that is logic 0. Again now this one entry, now this one when A equals to 0, B equals to 1 and C equals to 0, then again sum goes to 1 and carry goes to low, that is 0. There is no carry occur. Now fourth entry, when A equals to 0, B equals to 1, C equals to also 1, then we see that the sum goes to 0 and carry goes to 1. Again, when fifth entry, when A equals to 1, B equals to 0, C equals to 0, then output goes to, sum goes to 1 and carry goes to 0. Sixth entry, when A equals to 1, B equals to 0, C equals to logical 1, then again sum goes to 0 and carry goes to high, that is 1. Second last entry, when A and B are 1 1 and C equals to 0, then again sum goes to 0 and carry goes to high. In last entry, when all the three inputs A, B and C are 1 1, then sum goes to 1 and carry goes to also 1. So this is the two tables of a full adder logical circuits which having the inputs A, B and C. We take other variables also for the inputs like X, Y, Z, but here we take the inputs A, B and C variables. So now we develop the expressions for the sum and the carry out with the help of Karnaugh map, that is K map, because here the inputs are three A, B and C. So we develop the 8 cell K map for the sum and the carry out expressions. K map for the sum expression. K map for the sum expressions. Because again we have three inputs, so we develop a 8 cell K map. Here we take the B, C in and the inputs A. A having the values 0 and 1, B and C in having the values 0, 0, 0, 1, 1, 1, 1, 0. That's the 8 cell K map for the sum expressions. Since from the two tables we see that the sum is only 4 times high for the values of A and B and C. This one, last this one and this one. So we fill these entries in the K map cell when A0, B0, C in 1. A0, B0, C in 1. Here. A0, B0, C in 1. So this one set. This entry is completed. Now, when A equals to 0, B equals to 1, C in equals to 0. A0, B1, C in 0. A0, this one, B0, B1 and C in 0, this one set. A0, B1, C in 0. So this one set. Now third one entry is when A equals to 1, B0, C in also 0. This one set. And last entry when all the three inputs are high. This one's. So here in K-map we see that all four are individuals. There is no possibilities of any quad or pair in the K-map cell or any octet. So we make only four individuals here. This one, this one, this one, and this one. The answer for this one will be A complement, B, C in complement. Answer for this one with the help of the K-map after minimizing A complement, B complement, C in. And this one we have equals to 1. So A, B and C in are 0, 0. B and C in are 0, 0. So B complement, C in complement. Now last one is this one. So answer for this one will be, because all three variables having the high expressions means equals to 1. B and C in also 1, 1. So we write A dot B dot C in. So finally expression for the sum will be equals to the sum of for these individuals group. That means S equals to, sum equals to A complement, B complement, C in plus here A complement, B, C in complement plus A, B, C in complement and plus last term is A, B, C, A, B, C in. So that's the expressions for the sum. Similarly, we find out the expressions for the carry out with the help of the K-map. Now we develop a K-map for the carry out expressions. K-map for the C out. Now we develop the K-map for the C out expressions. So again we develop a 8 cell K-map for finding the expression for the carry out. B, C in A, A having the values 0 and 1, B in C in having the 4 values 0, 0, 0, 1, 1, 1, 1, 0. Now from the truth table we see that carry out is 4 times high. Here, here, here and here. So when carry is high, then the input combinations are A equals to 0, B equals to 1, C in equals to 1. Okay, so A equals to 0, C in equals to 1, B in equals to 1, this one and this one, this one. And last one is when second time when carry out is high, then input combination are A1, B0, C in 1. So we fill this in the K-map A1, B0. This one cell. Again, when C out is high, that is third times, then the input combinations are A equals to 1, A equals to 1, B equals to 1 and C in equals to 0. So A1, B1 are high and C equals to 0, this one cell. This one cell. And last one, when carry is high, then all three inputs A, B, C in are high. So this entry comes here. this one. So now with the help of the K map we make the pairs. This one, this one, this one. So here we see that only 3 possible pairs. So answer for this one is from the K map that becomes equals to B, C in. Answer for this one pair will be equals to A, constant is B, A dot B, and answer for this one pair will be equals to A and C. Simply A dot C. So finally the carry out expressions will be equals to the sum of these 3 pairs output. That's equals to so C out equals to B C in plus B dot C in plus A dot C in plus A dot B. So that's the final expressions for the sum and carry out in case of a full adder, where we take A, B, C in as a input. Now we develop the logical circuits for the full adder with the help of these 2 expressions, sum and carry. So this expression is again simplified, means since S equals to A, B, C in plus A complement B, C in complement plus A, B complement C in complement plus A, B, C in. So we take the common C, take a common. So here we get the A, B plus AB plus A dot B, and in last 2 terms we take the common C in complement, C in complement, C in complement, C in complement, that is A B plus A B complement. That is nothing but only C in equals to A X naught B and plus C in complement A XOR B. That's the logical symbol of the X naught, and it is the logical symbol for the XOR. Further, we simplify this one. So we get S equals to C in X plus C in complement X. That's the X complement, sorry. So C in X complement plus C in complement X, where X equals to A complement B plus A dot B complement. So if we put the values of A and B here, equals to A XOR B. Hence S equals to A XOR B XOR C in. That's the final expressions for the sum. Now we develop the logical circuit of a full adder. Because we have the XORing, that's the XOR gate of 3 input XOR gate. Inputs are A, B and C in. Output of this XOR gate will be equals to the S equals to A XOR B XOR C in. Now we see the C out. That is the C out. It equals to A dot B. That's the ending operation. Again A dot C in. Again it is ending operation. B dot C, it is again ending operation of B and C. So we develop the 3 AND gates here. Now, so on the first AND gate we have the inputs A and B. So we fetch the input from here. That is A, and we fetch the input from here, that is input B. So output goes to A dot B. A dot B. Now we take the B and C inputs for the AND gate second. This is the AND gate. AND gate. And gate 1, 2 and gate 3. Okay, for the third AND gate we take the inputs A and C. A and C. So that becomes equals to B C in, B dot C in, and it is A dot C in, A dot C in. And now in last this AND operation is completed. These 3 terms are ORed with the help of this logic OR gate. O. So here we get the C output. That's the final circuit of a full adder, in which we take the 3 inputs A, B and C in. You also take the inputs as A, B, X or X, Y, Z, W, anything. There is no problem in choosing the variables. So that's the final logical circuit of a full adder. Thank you.